Since my voice still isn't all that great, I thought it'd be best if I started actually recording some lectures. This will make it easier for you guys to hear me. You can view the material more than once, and we can cover other issues during class as we can. Um, Plus, next week I'm going to be gone both Wednesday and Friday, and I'm going to do video lectures for both of those days. We've already covered, but I wanted to go over again what magnets are, what magnetism is, and just talk about that one more time. We said before, while there were electric monopoles, and while you have for an electron, right, you have electric field lines coming off of it like this, or for a proton, you have electric field lines coming to it. Well, actually the other way around. Electric fields going off the proton, coming to the electron. When it comes to magnets, that's not the case. Magnets always occur as a dipole, as if you always had an electron and a proton together, so that the magnetic field looped from one to the other, and in fact all the field lines would be loops. Well, that's actually the case with magnets, that the magnetic field lines here go from north to south, looping around, so that you always have closed loops. It even goes through the material to get from one to the other. So magnetic field lines always have closed loops. We also talked about how magnetic fields arise from moving charge or you moving relative to a charge. Either works. And magnetic fields arise from the spin of an elementary particle or spinning charge, like an electron or a quark, a proton, W plus and minus bosons. You get a magnetic field from those. The spin of the electron, however, isn't really spin as we think of it classically, like a top spinning. If you were to take an electron and calculate the magnetic field you should expect from it, from a physical particle spinning, you would get a magnetic field that's half of what we actually observe. There are big experiments on measuring this difference, called the G-2 experiment, on measuring very precisely how close is that factor of 2 to the number 2. The G-2 experiment that was at Brookhaven National Labs when I was there was very large, about twice the size of our room, and they moved it in one piece from Brookhaven Labs to Fermilab by putting it on a barge, taking it down the East Coast into the Gulf of Mexico, and then up the Mississippi River. So, how do we make magnets? Or what makes a magnet? So most magnets are made from ferromagnetic materials, and we use the word ferromagnetic because iron or ferrum is the most common magnetic material out there. The reason iron is magnetic is because it has these 4 unpaired electrons in the D shell. If you look at the electrons and you look at the ones that are paired up, there's one like this and one like that, and essentially they have magnetic fields that cancel out. Well, the unpaired electrons then give you excess magnetic field. It's this magnetic field from these unpaired electrons that gives rise to magnetism in iron. When you put a mass of iron together, so you melt it or even just throw it together in chunks, each atom is its own little bitty magnet. And you can imagine, they're going to prefer to line up to some extent, but they have to overcome other forces to get there. What actually happens is magnets end up lining up in little subdomains like this. And so if you could look very closely, if you could map the magnetic field in the iron very closely, you would see these little subdomains. If we apply an external field to that, then more and more of them line up until eventually you get something that looks like a traditional magnet. Now, you can help it get there by using some heat, and in fact applying a little heat to iron will sometimes help those individual atoms overcome the bonds that are holding them in place and cause them to line up. However, too much heat and you hit the Curie temperature. At the Curie temperature, The kinetic energy in the atoms is too much. It overcomes all of the forces having to do with magnetism, and it's impossible to create a magnet out of material once it's above its Curie temperature. That temperature varies from material to material, and for some materials that temperature is below room temperature. Now, magnetic fields and moving charges. So when a charge is in a magnetic field and moving in a when it's moving in a magnetic field, if a charge is simply sitting still in a magnetic field, it experiences no force from the magnetic field. However, if the charge is moving, then experiences a force. And the way I think of it is, since the force it experiences is Q V cross B, I think of V as being the direction of my fingers, B coming out of my hand, so I'm doing a V cross B, and then the force is along the direction of my thumb, so V cross B with the force up in this case. If there's also an electric field present, then the total force is just the charge times the electric field plus Q V cross B. Now, when we talk about a current flowing in a wire that's in a magnetic field, then we'll begin to see what's called the Hall effect. Now, the Hall effect simply describes how those charges flowing in the wire respond to the magnetic field. You think about the current density. The current density is the number of electrons per unit volume times, times the charge of an electron times the drift velocity. You remember drift velocity from a few weeks ago. Times the drift velocity of electrons in the material. So for a magnetic field perpendicular to the current, as we have here, the force on a given charge is Q V B sine theta, sine phi. Phi is the angle between the magnetic field and the current. In this case, we have them perpendicular, so sine phi is 1. So the force on a given charge is E times the drift velocity times B, which we can rewrite as the current density times B over the charge density. The total force on a wire then is the total amount of charge in the wire, which is the current density or the charge density times the cross-sectional area times the length. That gives you the volume times the charge density. That gives you the total charge in a given length of wire. So the total charge in a given length of wire times the force on each charge gives us the total force on the wire. That works out to be N times the area times L times JB over N, which we can rewrite as ILB. Moving back to include the cross product, this can also be written as F equals IL cross B. And for non-uniform wires, you would look at this as DF equals IDL cross B. So if you had to integrate over a non-uniform wire, suppose a wire just wanders around through a magnetic field, you would use this to construct that integral. Now let's look at the torque on a current loop. Consider a current running through this loop. So it goes in this way and up and around and out that way. All right? That's the current. Now along the top, the current's flowing this way. And the magnetic field is this way. So I cross B indicates that the force on that part of the loop is downward. Along the bottom, the current is this way, and the magnetic field is still that way, and I cross B indicates that the force, let me change that, the force on this is upward, I cross B, upward. So we have a downward force on the top, we have an upward force on the bottom, those are the same, so the total force vertically cancels out. If we consider the sides, we have a different story. On the sides, You have a current going this way. You have the B field going that way. Well, I cross B indicates that the force on this one is into the screen. And on this side, I cross B indicates the force on this one is out of the screen. That corresponds to this and this. So we have a force. This is a top-down view. Down here is a top-down view. So we have a force exerting this direction and a force exerting that direction. So this wants to rotate. Now what happens when this rotates and you get up to where the current here, sorry, I did not mean to do that. Okay, so the current here and down here, so we've crossed the midpoint, and now this piece is swung down to here, and that piece is swung up to there. Well, if nothing else changes and the current's still flowing the same direction, the force is now in this direction, is still in that direction on that one, and the force is still in that direction on that one, and it would simply rotate back. So this, if you had it started it going, this system would just rotate back and forth and oscillate. Well, that's not what we actually do with these. What we actually do with these is set them up so that once they hit the midpoint right here, they use brushes at the bottom to change the direction of current flow, so that once it comes over to here, instead of the current, once it rotates down, once this rotates down to here, instead of the current being out of the screen at that point, instead of the current being out of the screen at that point, and instead of the current being instead of the current still being into the screen at that point and this being out of the screen, they reverse. So the brushes allow us to change the direction of current flow. And by changing the direction of the current flow, we keep this motor rotating in the same direction all the time. So B field from a current on a long straight wire. So we have, I'm going to skip down, we have here Ampere's law. Right? Ampere's law that the integral around a closed loop equals mu naught I. So if we look at the integral around this, the B field is constant in a uniform circle centered on the current here. It is always in the same direction by the right hand rule, and B dot dl just ends up being B R d phi, right? So we're going to integrate RB d phi. We're going to do 0 to 2 pi of R B d phi, and that is just 2 pi R B. So 2 pi R B equals mu naught I. That gives us the field from a current in a long straight wire is B equals mu naught I over 2 pi R. Mu naught, the direction is given by I cross R. Alright? So the current direction cross with the vector out to where the B field is gives you the direction of the B field. Mu naught is just the permeability of free space. It's 4 pi times 10 to the minus 10th Tesla meters per amp. And Tesla is the unit for magnetism. So if we consider the beam field at the center of a current loop, and here we're talking about, well, we are quite literally talking about just the very center of this circle. At the very center of this circle, the current around the edges is uniformly distributed. And we have the Biot-Savart law here. dB equals mu naught over 4 pi times I dl sine theta over r squared. Well, as you go around this, right, as you go around this, sine theta is constant. You're just integrating 0 to 2 pi r of mu naught over 4 pi I dl over r squared. And you end up getting B equals mu naught over 2 mu naught I over 2r. The B field at the center of a solenoid is another special case. Now, a solenoid, we actually consider a solenoid, when we talk about it like this, we consider it to be infinitely long. We know solenoid's not infinitely long, but and this therefore is really only an approximation. But the B field from a solenoid is mu naught n I. So how do we get that? So now we come to the infinite solenoid, right? And so if you imagine these being the wires wrapping around the solenoid, top and bottom, I'm going to set up B field because the solenoid is infinite, right? The B field only goes this direction, and because it's infinite, there is no B field out here, outside the solenoid. I'm going to go up here, across, down, and back, right? And this is some distance h. So that gives us, as a result, B, all right, if we do this integral, B dot dl, right? Across the bottom, we get B h. On the vertical pieces, here and here, we get 0, because there we're going perpendicular to the B field, and B dot dl is 0. And across the top, there's no B field, so that's 0. So that equals the current flowing through here. Now the current flowing through there is I times N, where N, well, and there's a mu naught I times N, where N is number of wires. Okay, so writing isn't going very well. Number of wires per meter, right? Times I. So that N H is the total number of wires. NH is the total number of wires. And this gives us B equals mu naught I times N. Okay. Last piece, talking about the force between two conductors. From before, the force on a current carrying wire to a B field was F equals ILB sine theta, or IL cross B. The B field on at I2 due to I1 in the picture is B1 equals mu naught I1 over 2 pi R. That's just the B field due to a current, infinite current. The force on wire 2 is then F2 equals I2 LB1, where sine theta equals 1. So F2 is mu naught L over 2 pi r I2 times I1. Now, the two forces are equal and opposite. So F2 equals minus F1. We'll just call it F and write it in terms of the force per unit length. So the force per unit length, F over L, is mu naught I1 I2 over 2 pi r. Okay. And that brings us to the end of that lecture. Oh. And none of that got recorded because I messed up. Damn it. Where's the recorder?